Many of us think of glass as a solid, a rigid material that holds its shape indefinitely, like a rock or a metal. However, scientifically speaking, glass isn't a true solid in the same way crystalline materials are. Instead, glass is classified as an amorphous solid, a state of matter that shares properties with both liquids and solids. The key difference lies in its atomic structure. Unlike true solids with their highly ordered, repeating crystalline lattices, glass has a disordered, random arrangement of atoms. Imagine a neatly stacked pile of bricks versus a random heap of pebbles. The bricks represent a crystalline solid, while the pebbles are like the atoms in glass. This means glass lacks a distinct melting point, gradually softening as it heats up rather than transitioning sharply from solid to liquid. At room temperature, glass is incredibly viscous, meaning its atoms move, but at an extremely slow rate, making it appear solid to us. This unique structure also debunks a common myth, that old cathedral glass is thicker at the bottom because it has slowly flowed downwards over centuries. While some old glass panes are indeed thicker at the bottom, this is due to the imperfect manufacturing processes of the past, not because the glass has flowed. Early glass makers couldn't produce perfectly uniform sheets, so the thicker, heavier side was simply placed at the bottom during installation for stability. The rate at which glass atoms move at room temperature is so infinitesimally slow that any noticeable flow would take far longer than the age of the universe. So, while glass feels solid and acts like a solid in our daily lives, its internal structure tells a more complex and fascinating story. It's a supercooled liquid, frozen in a disordered state, making it one of the most intriguing materials we encounter.